For centuries, astronomers and philosophers wondered how our solar system and its planets came to be. As telescopes advanced and space probes were sent out to explore, we learned more and more about our solar system, which gave us clues to how it might have taken shape. But were our ideas right? We could only see the end result of planet formation, not the process itself, and we had no other examples to study. Even with the knowledge gained about our solar system, we were left to wonder, are there other planetary systems out there? And did they form like ours? Discoveries made by the Hubble Space Telescope are helping us fill in key pieces to the puzzle of how planets form. As gravity pulls material in the collapsing cloud closer together, the center of the cloud gets more and more compressed, and in turn gets hotter. This dense, hot core becomes the kernel of a new star. Meanwhile, inherent motions of the collapsing cloud cause it to churn. As clouds get exceedingly compressed, much of the cloud begins rotating in the same direction. The rotating cloud eventually flattens into a disk that gets thinner as it spins, kind of like a spinning clump of dough flattening into the shape of a pizza. These circumstellar, or protoplanetary disks, are the birthplace of planets. As a disk spins, the material within it travels around the star in the same direction. Eventually, the material and the disk will begin to stick together, somewhat like household dust sticking together to form dust bunnies. As these small clumps orbit within the disk, they sweep up surrounding material, growing bigger and bigger. The modest gravity of boulder sized and larger chunks starts to pull in dust and other clumps. The bigger these conglomerates become, the more material they attract, and the bigger they get. Soon the beginnings of planets, planetesimals as they are called, are taking shape. The 8 planets in our solar system make up 2 different groups. The 4 planets closest to the Sun make up the rocky terrestrial planets, and the 4 planets farthest from the Sun make up the gaseous Jovian planets. Why do objects that form from the same cloud of gas have different compositions? The answer lies in where these objects formed in relation to the parent star, our Sun. The 4 inner planets are called terrestrial planets because their surfaces are solid and, as the name implies, somewhat similar to Earth. Although the term can be misleading because each of the 4 has vastly different environments. They're made up of mostly heavy metals such as iron and nickel, and have either no moons or a few moons. The outer planets, sometimes called Jovian planets or gas planets, are huge planets swaddled in gas. They all have rings and all have plenty of moons each. Despite their size, only 2 of them are visible without telescopes, Jupiter and Saturn. Uranus and Neptune were the first planets discovered since antiquity and showed astronomers the solar system was bigger than previously thought. The inner planets are smaller and closer to the Sun because they contain more mass. Because they have more mass, the Sun can easily keep them closer, and their gravitational pull on themselves is great enough to compress themselves. The gaseous planets are farther away from the Sun and larger because they have less mass, so the Sun can't hold them in as close, and their gravitational pull on themselves isn't as great, so they spread out and are less condensed. Inner planets contain air and water, and outer planets contain solid material. How did material transport between the inner and outer edges of our solar system? Astronomers believe that comets have played a contributing role in the transportation of elements to different planets. Comets containing rocky material may come off terrestrial planets and hit gaseous planets, as well as comets containing gaseous material and water hitting terrestrial planets. It all started with a stellar nursery. It was just full of dust, electrons, neutrons, protons, and eventually started collapsing in on itself. The next phase, a protostar, is when there is much pressure, however, there is no fusion yet. The main sequence star is when there is finally fusion, and protons and electrons collide to make atoms. A main sequence star can make a red giant or a supergiant. A red giant consists mostly of hydrogen but burns to produce helium. A planetary nebula is made when a red giant burns mostly all of its hydrogen, and all that's left is the helium in the atmosphere. Because of little gravitational mass, all that's left is a white dwarf, a hot corpse of what once was. A white dwarf can make a black dwarf, which emits very little to no light and is just a white dwarf but cooled down, or can restart as a protostar once more. This time, if we are to go the hot, fiery, sexy route, a protostar can become a main sequence star and then turn into a supergiant. Supergiants are the biggest, most luminous stars in the galaxy. They burn so hot that they end up dying much faster than other stars. A supergiant dies much more painfully and stronger than a red giant. It ends up creating a supernova. A supernova is an explosion that radiates as much energy as the sun or any ordinary star in its life. A supernova can have three outcomes. A neutron star, which is 8 to 20 times larger than our sun, and the protons and electrons are crushed together to become neutrons. Or you can get a black hole, which is 25 times the mass of our sun, an implosion so violent that it never ceases. Or it can become a protostar once more and begin the cycle all over again.